So you're listening to your favorite song on your favorite stereo, and then you hear this kind of buzzing noise, and then you hear a loud pop, and then everything goes quiet. How many of you have ever had that happen? So of course you check and you look at your speaker, and you find out that your 4 ohm speaker is now reading 767 ohms. And if you tap it, it goes all over the place. Yep, this speaker is blown. And the reason that these speakers blow is there's two main reasons. Number one is if you overload the speaker. In other words, you put way too much power than the speaker can handle. Because that can create heat in the voice coil and burn it up. But the other thing that can cause this is something called DC offset. And DC offset is a bad thing to put across your speakers. So this video, we're going to talk about DC offset. We're going to talk about the different classes of amplifiers and how we can get DC offset. Then we're going to actually bring in a receiver onto the bench and do couple modifications to it. And we're going to look at some of the ways that we can prevent this from happening to our speakers. So if that sounds interesting to you, stay tuned, and that's what we're going to be doing. Okay, before we start looking at some things, let me begin by saying this is another one of those very unscripted, fly by the seat of your pants videos. Again, things are very busy here at work and at home with life in general, and it just so happens that today my wife and daughters are out with my mother and my sisters and everybody at a function, and my son is sleeping in today because he was up all night with his buddies playing video games and things. So Bella and I have the house to ourselves. So she's up on the couch taking a nap and enjoying the quiet, and I'm going to stay down here on the bench and take a little time to play around. So again, unscripted video, and it is what it is. So the first thing I want to talk about is the different classes of amplifiers. Not every amplifier is built or designed the same, and we have to treat each of them different. So when we're troubleshooting these, we really have to know what type of amplifier we're working with before we can really understand where these problems that blow our speakers can come from. So this is our first very basic circuit. This is a Class A amplifier. And what that means is that this circuit, when it is turned on, this transistor is going to be partially conducting all the time. In other words, there is never a time from when you energize this circuit that it is not at least partially biased on. So if we measure this point here, which is going to be our speaker output, there will always be a DC level voltage here. In other words, and the way this is, if it's set up correctly, designed correctly, whatever your DC rail is, in a perfect world, during idle, with no signal applied to the input, you would want this to be about 1/2 of your rail voltage. And what that's going to allow is that if we have 12 volts up here, if it's sitting at 6 volts, we can actually allow the signal to rise up to our 12 volts, and we can allow it to drop to 0 volts. Hey, did you wake up? I know you're enjoying the day too. Say hi to everybody. Yes, this is Bella. Hi, baby. She is a Cavalier King Charles Spaniel, and she's spoiled. Okay, we are back. So, as we were saying, and this is how we get our AC sine wave. But here's the problem. If there's 6 volts sitting here at idle all the time, remember, speakers do not like DC voltage. And why is that? So when we have a speaker that's not burned up and we put our little ohm meter across the voice coil, we find that there's about 8 ohms there on this particular one, but they can fluctuate anywhere from 3 ohms up to 16 ohms, let's say. Either way, it's a very low impedance. And if we do the math, if we remember, current equals voltage divided by resistance. So if we take our 6 volts divided by the 8 ohms that we measured, we get approximately 750 milliamps of current. And if we use that to check the power, we know that P equals I times V, or current times voltage, which is our 0.75 amps, or 750 milliamps, times 6 volts, is about 4.5 watts. Okay? And yes, you can also you could rearrange it to figure the power directly, but I wanted to show you all the factors here. Now, what's the problem with that? You have 4.5 watts of dissipated energy in the voice coil of that speaker. And if you look under RMS AC conditions, you're only supposed to be able to have a maximum of 2 watts. So you're more than double exceeding, even with this tiny little amplifier circuit, you have more than 2 times the rated energy that this voice coil can dissipate. And remember, this voice coil is only able to dissipate this intermittently. In other words, it's designed for music where the signal fluctuates up and down. So it wouldn't be too long before the little thin wire that's wound around this voice coil would overheat and burn up. So, not to mention, you have a coil of wire wrapped around a magnet. That's what a speaker is. It's actually kind of a linear motor, right? So you have a magnet in here, you have a coil of wire that's situated around that magnet, and when you apply a voltage to that coil, it will set up a magnetic field an electromagnetic field that will oppose the magnetic field of the magnet. And it'll cause it to try to deflect one direction or the other based on the polarity of the voltage being applied to the coil. And that's how a speaker works. The problem is, if you put straight DC voltage, the speaker will deflect all the way one direction or the other and stay there. So now the speaker is not operating properly, and again, you're putting excessive current through that voice coil. It's just not designed to do that, and it burns up. Now, looking back at this circuit, we can see that there's a way to deal with this, and that is they placed a capacitor between this DC voltage here and the speaker. And capacitors can pass AC voltage, but they cannot pass DC voltage. So what will happen when you first turn the amplifier on, this voltage will go to 6 volts here, or to whatever it's biased to. That voltage will apply a charge onto the plate of this capacitor, and through this coil it will charge it up. So with this particular amp, the way it works, you'll hear a little pop when you turn it on. The thing is, as this capacitor charges, the closer it gets to that 6 volts there, the more the current will drop, and so the current through this speaker will only be for a very short duration, not enough to burn up the voice coil or hurt it. So you'll get a little pop sound, and then everything will stabilize, and eventually the voltage here will drop to 0 because the current will drop to 0 as the capacitor charges to the same voltage as this rail right here. And that's the whole principle of how these little Class A amplifiers work. This is called Class A operation, or single-ended operation. And so the only time after that point that you'll get any signal to the speaker is if you change the voltage here. Anytime the change of voltage happens here, that change will be reflected through the capacitor and through the voice coil to ground. So that's how you get your sound. So the AC will pass through here, but the DC won't. And that's what's very important. So our first lesson, if this capacitor fails, if it becomes leaky or it dead shorts, that voltage is now going to pass right across here like a dead short, and it's going to go through this very low impedance, and it's going to overheat the voice coil very quickly and cause it to fail. So this particular amplifier is not a very safe one. The whole safety of your speaker is dependent upon this one component, this capacitor. So this better be a very good quality capacitor or you might be buying a new set of speakers. Now another variation of the circuit would be, in place of the capacitor, to use a transformer. Now the nice thing about this is this transformer, this coil right here, almost acts as a short with respect to this circuit here. And no matter what DC voltage there is back here, it will never affect on a DC level anything here because it's magnetically coupled. And the only time you'll get a magnetic field here, a changing magnetic field, is if the voltage here changes. As soon as it's done changing, whatever's on the secondary of the transformer will change, or will stay the same. So essentially, this has a lot better protection for your speaker. The downside of it is the cost of this transformer is very expensive compared to just a capacitor. Now, if you look at a lot of the old car radios out there, the old AM car radios back in the day, a lot of them used this topology. They used a little transformer. Also, a lot of the little handheld pocket radios and so forth, or in the early transistor radios, would use this topology just because of how safe it is. Remember, early transistors, the early germanium transistors, had a tendency to leak. And when they leak, you can very easily get DC, and they would short and all kinds of things. So the last thing you want is anything happening here to get to your speaker. So this was a very good circuit for that. So you will see a lot of this in car radios and in older amplifiers, the Class A amplifiers. And even some of the push-pull amplifiers would use a different variation of this with a center tap. And you'd have a transistor up here, a transistor down here, and you'd feed your voltage into the center tap. But anyway, these ones are pretty safe. Your speaker has a very low probability of failing in this type of amplifier, short of overdriving the speaker. So you put a speaker that's too small for the output of the amplifier, of course, that's your only risk. So those are your Class A designs. And you can see they always have to have, what I want you to take away from this, they always have to have an isolation between your output transistors and your speaker. The next type of amplifier we're going to talk about is called a single supply push-pull amplifier. So this is a push-pull amplifier. In other words, you have a transistor on either side of your output going to your speaker. And I color-coded these pins here because they have some significance here. You really don't get the whole picture of what's going on here until we look at the next page. But we'll get to that in a minute. If you notice, these transistors, here's your outputs, and these are your drivers. And these drivers are connected in a Darlington configuration with the outputs for gain. So this is your voltage gain here. And then these actually are to handle the current. Okay, so these don't really have a lot of gain in the circuit the way they're designed. These do, and they work in conjunction with one another to amplify the signal and to supply the current that that very low impedance 8 ohm speaker is going to need. The problem is, if we go through and look at this circuit, all the voltage is on one side here. So you have 50 volts here, you have 0 volts here, your actual ground or your common. And so in order for this to work properly, almost like a Class A amplifier, but this is not Class A, it's Class AB, and I'll tell you why in a minute. This center point is always going to be turned on. So there's always going to be a voltage, and it's probably going to be about half of your rail voltage again. So if this is 50 volts, in a perfect world with no resistance or anything like that, this would be sitting at about 25 volts, and it will swing up and down with respect to that. And what we're doing here is, through this little biasing circuit, you're actually turning these transistors partially on. So what's happening is, whenever one transistor turns off, the other transistor is already turned on. So there's like an overlap. So that's what this bias circuit is doing. It's ensuring that neither one of these transistors ever turns off 100% before the other one turns on. So there's a short duration in that AC sine wave, in that signal, when both transistors are conducting at the same time, and then the one will hand off the signal to the other. That's the best way to describe it, I guess. And this is nice in that you only need a single power supply. It's not as efficient because, once again, the maximum signal you can get is 1/2 of this, and minus all of its losses. Now, you might say to yourself, well, heck, if there's always 25 volts here, that's really going to fry the speaker, because we know with 6 volts, we were already putting out 4.5 watts across an 8 ohm speaker. What the heck is 25 volts going to do? Well, you do the math. So let's look at page 2, and things will become a little clearer. So, kind of move this over here. If we look here, here's my color codes, and if we look over here, you can see that the center point, the midpoint of your push-pull output section, comes straight out, and guess what? Just like this amplifier, it goes through an isolation capacitor. Now this capacitor is a lot bigger than that little Class A, because this is a higher wattage amplifier. I think this amp is rated at something like 20 watts per channel or 15 watts per channel, something like that. And it actually goes straight out to your speakers. Okay, so you have your speaker selector switch, and then it goes out to speaker A, speaker B. Here's your ground. Okay, and then if you look, pins 7 and 8, which is the other side from where your 50 volts goes straight to ground. So you're essentially connecting your speaker between ground and this capacitor right here. So if we were to draw that on here, we would go through a capacitor. Okay, and then we would have our speaker, and it would look like that. So there it is. So this is essentially what's happening, and this, once again, you have a capacitor isolating that voltage. If this capacitor fails, there is nothing to stop that voltage from going straight into the voice coil of your speaker and damaging it. And we call that DC offset. Okay, DC offset. In other words, it's offset from 0 volts. In other words, there is a voltage on here that shouldn't be. And that voltage will actually burn up this speaker. So whenever you're servicing these amplifiers, these either Class A amplifiers or these push-pull single supply amplifiers, the critical thing you have to look at is this capacitor. If it fails, there is no protection circuit to stop that voltage from going right through this shorted capacitor and right through your speaker and damaging what may be a very expensive set of speakers. So these amplifiers, you really have to have a very high quality capacitor right here to make sure that you never have a problem. This is one of the cases I will make for why you change certain capacitors, if not all of them, when you restore an amplifier. There's a lot of arguments can be made for signal capacitors that don't change bias or anything, whether you know they're still good and so forth. But this is one that unequivocally I would argue you should always replace with a good quality new capacitor. Get the correct one. Usually you want to use a low ESR value capacitor, one with a very high life and so forth. Make sure you look up the characteristics of the one that's in here and replace it with something similar or better. And you even though the cap may be good microfarad wise, it may have developed leakage with age, and that any amount of leakage will result in a DC offset. Even if it's only a volt or so, it'll be there, and it'll creep up with time as the capacitor ages. So there's your first thing you want to remember when you work on any vintage gear that uses an isolation capacitor like this, or a decoupling capacitor. Okay, our next one is one of the scarier designs out there, because if you look here, here's your power supply. I'm sorry about this, the print isn't real clear on this one. But you have your power supply, this winding of your transformer. You have the center tap going to ground, and then you have these two going through a bridge rectifier. And you're developing what's called a split rail or a dual power supply. So one of them is a positive voltage, the other one is a negative voltage with respect to ground. So if you look here, we have a positive 27 volts and we have a negative 27 volts, and that positive and negative 27 volts will come down here and go into either side of your power amplifier section. If we move here, a little bit bigger view of it, here's your positive 27, and it goes into an NPN transistor, and you have your negative 27 volts going into a PNP transistor, and we still have our little Darlington set up, we still have our little bias set up, but now we are turning both of these on the same way, where they will hand off to one another, but the net value here is always going to be 0. So if we turn, basically if we turn this one on and turn this one on at the same time, you have a positive and a negative voltage turned on all the time. And if you turn them both on the same amount, essentially what's going to happen is the net result at the center of it with respect to ground will be 0. And only if one voltage changes, becomes higher than the other, so this one goes more positive than this one is negative, or this one goes more negative than this one is positive, will you have any voltage here. Now this is the scariest circuit, and I'll tell you why here in a second. So what's happening is, whenever you apply your input, your signal to the amplifier, if the signal swings positive, this transistor will be driven harder, and it will allow this to go more negative, I believe, if it's inverting. I'd have to go through this. Some of them invert, some of them don't, depends on how it's designed. And the opposite happens when this signal swings negative. So essentially, by turning one on more and off more, and this one on more and this one off more, and so forth, alternating back and forth, we are creating an alternating voltage here. And when the thing is sitting idle, there's nothing here. So there's no need to have an isolation capacitor. So if we look back here at the circuit, we come straight out of this little snubber network right here, you see. This is to prevent the amp from going into oscillation and so forth. More, that would be another video. And come straight out through a little 3 amp fuse through your speaker selecting switch and out to your speaker terminals. Now, here's the problem. What happens if one of these transistors should short? All of this voltage is going to go straight to here. It's going to go straight through here, straight out here, and straight to your speaker. And your speaker is going to have to sink all of that current. And if the current is less than 3 amps, this fuse will not blow. So really what they're relying on is if you have a really hard short, for a short duration, you'll exceed that 3 amps and you'll open the fuse hopefully before you open the voice coil in your speaker. Now that's a big chance you're taking, but theoretically you could do that. This is why you never, when you see a blown speaker fuse in this type of amp, you never put a bigger fuse in. I always start out by putting a smaller fuse. Actually, I do other things, but you do not want to put a bigger fuse, because here's the problem. These don't always go dead short. Sometimes these transistors will leak, meaning they will partially short, and they will, even especially one of these drivers back here, if they partially short or they go leaky, it will turn it will change the bias of one side. It'll bias it one way or the other, so there will always be a DC offset there. And that offset is going to go straight to your speaker, and if it's small enough, it may not take out that 3 amp fuse. So it will be enough to overheat the voice coil of your speaker and burn it up, but it won't be enough to cause that fuse to blow right away. That's the worst possible scenario you could have. Now, this particular amplifier just doesn't have any protection other than that fuse for the speaker. Now, what other amplifiers do is they put a little circuit in there to monitor the DC offsets. Let's look at that next. Okay, so here's a little block diagram of what I'm talking about with a protection circuit. So the power amplifier is just the same thing as the one we just looked at. However, instead of coming out of the amplifier module and going straight into the speaker jack, it goes through your snubber network, but it now goes into a relay. And that relay then, the contacts of the relay then will go to your speaker switch, which goes to your speakers. And if you look up here, there's a little circuit. And this actually is a lot more advanced than some of the other ones. But one of the functions of this circuit is to actually measure that DC offset. If it sees see there's a little sampling that comes up off of here from these little resistors. And if there's any voltage on here above a certain threshold, and usually that threshold is about 1 volt or less, it will actually trigger this circuit, which will drop out this relay. And that's the whole purpose of it. Now, this circuit can do more than just that. In this particular amplifier, not only will it check for DC offset, but it also can monitor the current flowing through the amplifier circuit. So if you have an excess of current feeding into the output transistors, that would indicate an overload situation. So say your speaker is actually shorted, or you short your speaker terminals. That's going to draw excessive current through those transistors, and it's going to cause them to fail. So what this thing does is it also monitors the peak current, and if that current exceeds a threshold, it's going to drop out the relay. The other thing it's going to do is when you first turn these amplifiers on, you can once again get that pop into your speaker, because those two output transistors are not going to have exactly the same slew rate, meaning they're not going to both turn on at exactly the same time. So there is going to be a short duration where there is going to be a DC offset during power up until everything kind of stabilizes, which will cause that loud popping noise. So if you hear some of the lower cost amplifiers out there, you notice that in some of them, when you turn them on, they make a loud pop in the speaker, and then it's okay and everything works perfectly. That's because there is no protect circuit. What this thing will do is actually, when it senses the amplifier being turned on, it will wait a certain amount of time, usually a couple of seconds, before pulling in this relay. And then if everything's good, there's no DC and there's no excessive current, after that delay, it'll turn this on. That delay also serves that if you have a short-term short on your speaker terminals, it allows the amplifier to automatically reset itself. So when the short goes away, it counts off that little delay and then brings the relay back in. So it's a pretty cool circuit, and that's what these do. So we're going to look at some of these things now, and we're going to look at the amplifier that we just looked at the schematic on that does not have the protect circuit, and we're going to end by adding a little protect circuit to the amplifier. So we're going to use this receiver here. It's a Pioneer SX535, and it's a low-powered receiver. It's one of the lower-end ones, but these actually are very good sounding amplifiers when they work properly. And they're only rated, I think, at 20 watts per channel or 22 watts per channel, something like that. But with an efficient set of speakers, these things sound amazing. They work really well. However, there are some shortcomings in them, and the reason I chose this receiver is because most of the problems that you can encounter in these kinds of amps exists in this particular model. The first thing we need to look at is some of the transistors that are problematic in these. When you look at this schematic, and yes, that is the schematic we were using as an example, a few of these transistors have known manufacturing flaws in them. In other words, they were good transistors, but they are prone to failure, and their failure mode is they will get noisy and leak. In other words, they won't always go dead short, although sometimes they will. But what they will do is they will leak. In other words, they will partially turn on even when they're not biased in a way to turn on. And that will cause this whole circuit to be offset to one side or the other, and will cause DC offset to take place here. Again, you have a 3 amp fuse in here. So chances are, if this only goes partially out, you won't draw 3 amps through your speaker, but you don't need 3 amps of current to damage your speaker, especially if they're smaller speakers like you would see on a smaller receiver like this. So that's a bad situation. Not only that, it causes distortion, all kinds of other things. So the first thing we want to do is we want to identify those bad transistors and kind of do a little bit of preventive maintenance by replacing them. And really one of the big culprits are these 2SA726s. And you see I put a little check mark next to those. Anytime you see these units that have these 2SA726s, and there are a few others out there, you pretty much want to replace them, at least in the amplifier circuit, to save yourself grief down the road. And this is not a shotgunning thing. This is actually a really well-known, well-documented issue with these transistors. A very high percentage of them will fail. And anytime you have a situation like that, you don't want to put a lot of time and effort restoring your amplifier and so forth, only to have a 50-cent transistor cause the whole thing to fail and burn up. So that's your first thing we're going to do. And the second thing we're going to do is we're going to build this little circuit, which is actually a speaker protect circuit. It's very similar to the one we looked at the block diagram of, but it's an add-on that you can buy through eBay. We'll talk more about that when we get to it. And we're going to put this in there, and that's going to kind of give us some more assurance that if we have a failed transistor, or we have a shorted speaker terminal, we are not going to damage the amplifier, and we're not going to damage the speaker. And that's kind of what that's all about. Okay, looking at the inside of the receiver, this thing looks pretty clean, and it doesn't look like anything's been done to it yet. It does not look like the deoxit monster has been in here with the can of deoxit wildly spraying all the boards, which I really like that because it's not all dusty and gummy. Let's look at these transistors. Now, the ones that are in question are the 2SA 726s. Those are the ones that are bad. And those are usually going to be found in the input differential pairs, which are these little ones right here. So let's take a look at those and see what they are. Okay, if we look right there, those look to be 2SA 763s, which is good news because those ones actually are not that bad. They don't have a whole lot of problems. Now, something I want you to take a look at very closely. This might be interesting. If you look, let's see if I can get in here. If you look right here, where am I at? Right here. See it? I'm touching the leg. Notice how that leg has that black on it. That's not tarnish. Notice how there's a very distinct line there. That's actually black paint. And some of the later transistors that Pioneer and some of these other companies were using after some of those problems were happening, they actually put that paint on there to prevent the tarnish, because it's that tarnish that gets on the metal of the legs that kind of creeps up into the case of the transistor and a lot of times causes them to be noisy or leaky or whatever. So when you see that, don't mistake that for tarnish. If this were tarnish, you would actually see that black stuff all the way down. And notice how it's kind of the wire is bare where it enters the PC board and goes down into the hole. So kind of a little difference. Again, these transistors are very reliable, and very rarely do you have to replace those ones. It's the ones that, like what we talked about, the 2SA 726s, those ones are the older types, and those are the ones that tend to have the problem. So this is good news. Same thing with these other ones here. These are all good transistors, and I don't know if we can see the part number for those, but you can kind of see them in there. 2SC 1509. Those are, again, very good transistors, and these 2SA 777s are very good as well back here. So bottom line is we should not have to do any kind of preemptive thing replacing these transistors because they're actually going to be okay. Okay, the first thing, since this receiver does not have a speaker protect circuit, I want to check for DC offset on my first power up. So not only are we going to use a current limiting device, which in our case we're going to use the dim bulb tester, we can also use a variac and bring it up slowly. It really doesn't matter either way. Now, there are instances where you cannot use a dim bulb tester or you cannot use a variac, and it has to do with the bigger receivers, some of them that have these soft start circuits and so forth. It's really too much of a tangent to get off on to talk about that for this video, but just understand there are some reasons why you would use one power up device over another. We're just going to use the dim bulb tester. That's going to be just fine, and we're going to look at that output. So on this receiver, there's a really convenient test point. You have point number 1, terminal 1, and terminal 7 on the amplifier board. And if we move our camera over here, we can actually see it. Right here, there's 7, so that's for the right channel, and right here is pin 1 for the left channel, and then we can reference to ground, and that should be pretty easy. And then we can power this thing up, and this actually is before the speaker select switches, so we're directly checking our DC offset right here. So let's hook up a meter and check it out. Okay, the meter's connected to the right channel. We're going to check that one, and then we'll move to the left channel. And we're going to just bring this into range here, and we're going to start out in the volts We're just checking DC volts. And we're going to use our dim bulb tester. In case something is shorted, all the current will go into that light bulb filament rather than into the other components of this receiver and cause things to short out. So I'll show you that. Okay, so this over here is my dim bulb tester, and it consists of an outlet, a bypass switch where I can bypass the light bulb and just go straight through, and then we have this light bulb in this socket up here, and the light bulb is in series with the hot prong of this outlet down here. Now I also have it plugged into our little kilowatt unit, and I have it set to watts so we can actually see if there's any high current being drawn. Now the size of light bulb is going to be dependent upon how big of a device you're going to power up. This amp is very small, low power. If we put a 100-watt bulb in there or something, it would almost not light at all. So this one is like a 40-watt bulb, and it will light up, and then it should dim back down after the capacitors in the amplifier have charged up. So we're going to check this, and we're going to check our bulb at the same time and power it up, and we're going to see what we get. So here we go. And there you go. It's turned on, and we're drawing about 12 watts. And you can see our lamp is very, very dim. You may not even be able to see it on the camera. So that's very good, because that means that we don't have any excessive current being drawn at all. And if we go over here to check our DC offset, that equally looks good, because we only have about 38 millivolts on our speaker terminal. And if we go to the left channel, let's see what it has. It only has about 16 millivolts. So there's no major, that's all good. So there's no major DC offset on our terminals, on our output. So I think this amp is safe to power up without any current limiting or anything. So we're going to do that now. Okay, so we're going to check the output of the amplifier next. Now that we know that it's safe to connect a load to it, we're going to connect our dummy load. And I very often get asked about a dummy load, what it is, where to buy them, how to make one. I'm going to show you one of the early ones that I've used, and we're going to use it today. And it's very, very simple. So if you look, you have two resistors here. And if you look, they are rated at 100 watts, 8 ohms. Okay, so these are 8 ohm resistors, 100 watts, and they are non-inductive, meaning they do not have a reactive component to them, or the reactive component is so small that you would never notice it. Now, the way a resistor works is the way a resistor works in general is it converts power into heat. So whatever power you want to dissipate into the resistor is just going to take that power and convert it into heat energy. So it changes it from electrical energy to heat energy. As a result, these things are going to get really hot, which is why they have these little mounting tabs. So for them to work at their best performance, they kind of need to be mounted to a heat sink. And here's a very simple way to do it. So if you can scavenge an old computer, it doesn't really matter, just any old computer with a microprocessor on it. Most of them will have these really nice aluminum heat sinks. Some of them even have copper heat sinks. And most of them will have a fan attached to that heat sink. And it's really convenient because these are 12-volt fans. And what I've done is I've just drilled and tapped a couple of holes in here, and I mounted these with some heatsink grease onto this CPU heatsink. And then I've just attached the leads, or the wires from the fan, onto just a set of banana plugs, and then we can just plug this into our power supply, and we can run it anywhere from 5 to 12 volts if you want to run it low speed or high speed. Of course, you run it at 12 volts, the fan's a little bit noisier. And what this will do is, even though this is a really tiny compact thing that fits in the palm of your hand, I can actually run a 100 watt per channel 8 into 8 ohms amplifier on this, and it can easily handle all that power. And I have done that. I have run these at 100 watts per channel with the fan on, and they do get warm, but they won't burn up. So for how small and efficient this is a really good way to build a very simple dummy load. Now, if I attach these wires so that you can connect them right into your speakers or your speaker terminals, and then I put these little loops on here that you can connect your oscilloscope. So if you want to check, on either side of your scope, you can actually check the outputs. Now remember, if you use a 2-channel oscilloscope and you connect your ground leads from your scope probes to each of these, remember you are tying the grounds of those 2 channels together. Now most amplifiers that's okay. Like this one, it's okay. But some of them, like the Carvers and so forth, have isolated grounds, and you really can't do that without causing a short. Okay, so we have the dummy load connected. You can see we just have the little fan running at 5 volts right now, so it's nice and quiet. And I just have the oscilloscope connected on our little loop wires. And the speaker cables just go over to the speaker terminals. And we're looking at our oscilloscope here. Let's see if we can get a good... There we go. And let's turn this up. So you can see we have a nice looking sine wave. And there's no DC offset because we checked that. But now we're going to talk about another type of DC that can kill your speakers. So if we keep turning this up loud enough, as you can see, the signal gets extremely distorted. And those flat tops there that you're seeing, you guessed it, is DC power for that duration. Now that's very bad for speakers, especially your tweeters. It can damage them. Especially at higher frequencies. And so once again, there's no protection on this amplifier to protect against that. And by the way, I had that volume turned up very loud, and even though there was DC showing up on that signal on the output across your speaker terminals, the fuses never blew. So those fuses really don't do you much good when it comes to doing damage to your speakers. Now remember, this is a smaller amplifier, but even the big ones, when they don't have speaker protect circuits on them, this is what can happen. So that's why we're going to build this little circuit board here. And that's what we're going to finish off this video with. We're going to build this little speaker protect board. Not only will it protect against DC offset, but it will also cut out if you have too much DC in your signal by turning the volume up too loud. So this is actually going to protect your speakers. And that's one of the reasons we use these things. So let's get this little thing out and look at it, and we'll put it together. Okay, before we put this together, these things here are available on many of the haunts that we find online, like eBay and so forth. And I'll try to put a link to a couple of them maybe down in the comments section below. This is one of the smaller ones, and for this little 20 watt amplifier, this is more than adequate. I mean, these are good for 50, 75 watt amplifiers, something like that. They will work. They also make them in larger kits, larger circuit board, and much bigger relays and so forth, and a little more robust circuit. and they obviously cost more, but these ones here work really well for the smaller receivers, and they don't cost a whole lot. They're quite inexpensive. So we're going to put this one together. The only thing that this really requires of your amplifier is it uses a 12 volt power supply, and it uses one of those 7812 linear voltage regulators. There is a bridge rectifier that comes with it, and they recommend somewhere around 12 volts AC input, although you can go a little higher than that. Just remember the limitation of a 7812. I think the highest voltage that you can put into one of those is somewhere around 28 to 35 volts, something like that. So you don't want to go much higher than that. And just remember, the more voltage that this regulator has to drop, the more temperature that it's going to have to deal with, because basically what it's doing, just like resistors do, this linear regulator will actually convert that excess voltage into heat. So the more voltage you're dropping, the more heat that this thing's going to produce. So if you can find a 12 volt AC power source in your amplifier, that would be ideal, but you can go a little bit higher. Also, if you have a 12 volt DC supply in your amplifier, and it can handle the little bit of extra current that this will draw, which is not a whole lot, you can just directly connect that in here, I'm sure. Now when you get these things, at least the ones that I purchased online, these are only maybe less than $10, $5, something like that US. But what you're going to get is not much information, and it's going to be in Chinese. So you can Google Translate it, which I've done. Hold on. Right here. And it just basically explains how the circuit works. So I'll put this down here, zoom in on it a little bit, and you can maybe kind of pause the camera if you want and read through it if you'd like. Again, it's not a perfect translation, but it's a general translation of what's written on that little sheet. And you can see, I'll give you a little picture of this as well. Unfortunately, they don't give you an actual schematic of the circuit. That would have been nice, but this is all you get. So anyway, it's all silk screened. It's very easy to see the screening on the board. So we can just put these components in here. I'll solder it together, nothing special. You've seen that before. And once it's together, we'll be back. Okay, so here's the completed board all put together. And before I install it here, I'll just show you, I did make a little modification to the board. And that is, I put this heatsink on this voltage regulator, and the reason for that is we're going to use the 27 volt DC power supply off of this power supply to feed this. And since we're going to be dropping, the absolute maximum rating on a 7812 linear voltage regulator is about 35 volts input to get your 12 volts output. And so anytime you're dropping that kind of voltage, after it goes through these two diodes in this bridge rectifier, and yes, you can use AC or DC input on this, but once it goes through those two diode drops, you'll have somewhere around 26, 27 volts. And that's a good bit you're dropping off. So this heatsink will help it to stay cool, even though we may not need it. This is a very low current circuit. Now, in order to fit this heatsink, I had to relocate two of the capacitors to the other side of the board, which is what I did here. And that won't hurt anything because that'll just mount right back here. The other thing is, if you notice, these two screws stick through for the little tag, the serial number tag, and they just happen to be the same thread pitch as these little standoffs. So I used one of those, and then the only invasive thing I did was I drilled two very small holes up here to mount the board. This is all going to be totally reversible, with the exception of those two screws, which are black. They match. You won't even notice them. So we can take this back out if we ever want to. We'll go on the underside in a minute, and we'll look at how that's wired up. and how we connected these. But really the only thing you have is your power wires, your speaker, your inputs from the amplifier, and your outputs to the speaker, and then a common ground to reference to. And that, so we're in the underside of the amplifier, and right here is the fuse socket. Right, you take this little cover off and there's two fuse sockets here, and here's the back where the speaker leads go right in. So you have these two white wires here and these two orange wires, and all I did was I soldered a couple of wires onto these terminals and removed the actual fuses. So I took them out, so there won't be any fuses in here anymore. And then this is going to go up on the top, and I'll show you what we did to mount the board in there. The other thing is, if we go up a little bit further, I was able to pick off chassis ground right here. You can see the little wire connected. It goes down, and again the speaker terminal negative is also connected to chassis ground, so that's no problem at all. And again, this black wire is only for a reference, so the circuit can have a complete circuit to measure the actual speaker load and so forth. Okay, so the little module is in place. Let's turn it on. And you can see when the red light goes out, that means that we've come out of Protect. Now, I had one problem with this. If you notice right here, I have removed the two of the 100 microfarad capacitors. These capacitors are responsible for determining when the Protect circuit trips and how much DC is allowed for how long before it'll trip. On a large amplifier like 50 watts or so or bigger, these are the correct values. But since this is a low powered amplifier, only about 20 watts, with these capacitors we could never get the Protect circuit to trip when you were going into a real, bad clipping. And one of the things this thing is supposed to do is it's supposed to trip when the amplifier goes into hard clipping. So we're going to look at that now. Basically what I did was I had to replace those with 10 microfarad capacitors. So I went down by a factor of 10. And that is something you need to know with these modules. Those capacitors that come with it only will work with certain amplifiers. If you have a higher powered amplifier or a lower powered amplifier, you may need to reduce that. And if you have a little bit higher powered amp, you may need, and it's tripping a little bit too soon, you can increase the capacitance a little bit, and that will adjust it. So let's get over to the scope and take a look at how it works now. All right, we're hooked up, and if we bring the volume up, you can see it works just fine. And then we get into clipping, and if I go real easily, it won't trip right away. But if I bring the volume up quickly, you can see it clipped right out. And again, I can make it even more sensitive if I wanted to, just by decreasing the capacitance a little bit more. So if one of those transistors were to short out and put real hard DC on there now, it would cut that off, and it would not allow, and you see how quickly it reacts, and it will not allow the speakers to see that DC voltage, so it's going to protect your speakers. And that's kind of how it works. So again, you can experiment with those two capacitors on there. If you want to learn a little bit more about that, you can check my video. I think I talked about it a little bit on the Sansui 9090 restoration video. We got into that a little bit. We modified that circuit a little. So there you go. Once again, I hope this is helpful to you guys that are working with these amplifiers and kind of want to be able to add speaker protection and kind of understand how the amplifiers work, which amplifiers need this type of protection and which ones don't. A lot of the higher end receivers already have that circuit built right into them, but for the lower end ones like this, you don't. And these are the ones that'll kill your speakers because they don't have any protection. So hope you enjoyed it. Like I said, quick unscripted video here on my free time. I wish you all peace, joy, happiness, and good health in your lives. And until next time, we'll see you soon. Take care. Bye-bye.